This is Geometry, Unit 2, Lesson 3, on definitions and drawing conclusions. Definitions are very important in geometry because they allow us to draw conclusions based on what the definition says. So it's very important to have a precise definition. And in math, a precise definition should work both ways. So let's look at a couple of definitions and see if they are precise, good definitions. If we look at our first statement here, we have a triangle is a polygon with exactly 3 sides. Now, if this is true, if this is a good definition, we should be able to reverse it and have exactly the same thing be true. Let's see. If a polygon is a triangle, then it has exactly 3 sides. Is that true? Yeah, it is. That's true. Now, if I switch it around, if I say if a polygon has exactly 3 sides, then it's a triangle. Is that also true? Yeah, and that's always going to be true. So, this is a good definition of a triangle because it works both ways. If I have a triangle, it must have 3 sides, and if I have 3 sides, it must be a triangle. So this is a good definition of a triangle. Now, let's look at this statement. A square is a polygon with exactly 4 sides. Now, let's see if this works both ways. If a polygon is a square, then it has exactly 4 sides. Is that true or is that false? Well, that's true. A square has 4 sides, so that is true. Let's see what happens when I switch it around. If a polygon has exactly 4 sides, then it must be a square. Is that always true? No, that's actually false, because what else could it be? It could be a trapezoid. So if it's a trapezoid, is it a square? No. Okay. Anything with 4 sides, if it's a parallelogram, that's a 4-sided figure, but is it a square? No, it's not. So there's lots of different ones. So this is not true all the time. This is false. So this is not a good definition of a square because we could substitute other things in there and make it a false statement. So this is not a good definition of a square. So it's very important to be precise when you are looking at definitions because we want to get as much information out of it as we can. We're beginning to write proofs, and the first part of writing proofs is being able to draw a simple conclusion. A simple conclusion uses definitions that we know in order to draw a conclusion based on the information that we're given. Now, a given statement in proofs is assumed to be true. So given is what you know for sure. We know this is true. So let's take a look at this first statement. Given M is the midpoint of AB. Here's my picture right here. And here's M. That's my midpoint. Okay, now, what do we know about midpoints? Well, what does a midpoint do? Well, we know that a midpoint divides a segment into 2 congruent segments. So we know that is my reason that I can say whatever conclusion I'm going to have. A midpoint divides a segment into 2 congruent segments. Okay, so if I know this midpoint is going to divide segment AB into 2 congruent segments, what conclusion can I make about AB? Well, it's divided into 2 congruent segments that are AM and MB are congruent. That is our conclusion. Notice our definition of a midpoint is the reason we can say that AM is congruent to MB. So when you are drawing a conclusion, it has to be based on facts that you know. So a definition is a fact that you know. Let's look at this next given. We are given segment PQR, and PQ and QR are congruent. So what conclusion can we draw? Well, let's see. We have 2 segments that are congruent, that are part of the same segment. What does that tell you about Q? Well, that means, isn't that the reverse of this one? A midpoint divides a segment into 2 congruent segments, so if a segment's divided into 2 congruent segments, there must be a midpoint, right? Yeah, so it works both ways. A midpoint divides a segment into 2 congruent segments. So this was divided into 2 congruent segments, so what is your midpoint? If we look at our picture, since we know that PQ and QR are congruent, that means that Q is the midpoint of PQR because it was divided into 2 congruent segments, so therefore it must be a midpoint. Remember, a definition works both ways. If we have a midpoint, it makes 2 congruent segments. If we have 2 congruent segments, then you have a midpoint. All right, let's see if we can figure this one out. we are given that the measure of angle ABC plus the measure of angle XYZ is equal to 180. All right, what is it called when you add two angles together and you get 180 degrees? Well, that means that the angles are supplementary, because supplementary angles add up to 180 degrees. Supplementary angles add up to 180 degrees. That's our definition. So, if ABC and XYZ add up to 180 degrees, they must be supplementary to each other. Angle ABC is supplementary to angle XYZ, based on that definition. Since these two angles add up to 180, they must be supplementary to each other. That is based on the definition of supplementary angles. That is our reason. Definitions are handy because they actually can give us many conclusions to work with if we know how to use them. So let's look at angle JKL. Angle JKL is a right angle. So to show this is a right angle, I'm going to put a little box in the corner. So here's angle JKL. So what conclusion can I draw about JKL being a right angle? Well, what do we know about right angles? Well, we know that right angles measure 90 degrees, right? So our reason would be right angles measure 90 degrees. So what measures 90 degrees? Oops, right angles measure 90 degrees. Sorry about that. Right angles measure 90 degrees. And what is a right angle? We would say the measure of angle JKL is equal to 90 degrees. Reason, because right angles measure 90 degrees. We know that. All right, now what else do we know about right angles? How are they made? Well, if I have JK and KL here, and they're put together to make a right angle, what do we know about JK and KL, the segments? Well, they must be perpendicular. We know that perpendicular lines, or segments, perpendicular, can't spell, perpendicular lines make right angles. All right, so we know that JKL is a right angle, so what perpendicular lines made it? JK segment is perpendicular to KL. Those two segments together made the right angle, by definition of what perpendicular means. All right, now notice the rest of this picture. JKL is part of a triangle. And if angle JKL is a right angle, what kind of triangle is this? Well, it must be a right triangle. So triangle JKL is a right triangle because right triangles have right angles. Now, we've actually drawn three conclusions just based on the fact that JKL is a right angle. So, if you know your definitions, a lot of times they can apply to more than one thing. It's always important, too, to use your diagrams that you're given that goes along with the given statements. So, if we know that PQ is congruent to QR, looking at our picture over here, PQ is here, QR is here, and they're congruent. Now, notice this is a triangle. What kind of triangle has two congruent sides? Well, it's isosceles. An isosceles triangle has two congruent sides. So if this has two congruent sides, what's the name of this triangle? Triangle PQR is isosceles. So because this triangle has two congruent sides, it must be isosceles. Notice I am naming the triangle that has that, and that's my specific conclusion based on this reason. So remember, your reasons are your definitions, and then your conclusion is based on that definition. Now, you have to be very careful about what you're given when you're doing these kind of problems. If you are given that BD bisects angle ABC, all right, so you have an angle ABC, which is right here, ABC, that's that angle right there, and then we have segment BD that bisects that angle. Now, what does a bisector do? Well, if it's an angle that's being bisected, a bisector divides an angle into two congruent, well, if you bisect an angle, what do you get? You get two congruent angles. Okay, so if you're dividing an angle, you get two congruent angles. So if this angle is being bisected, what two congruent angles are there going to be? Well, if this is the angle that's being bisected, this angle here and this angle here would be congruent. So that means angle ABD, this angle here, is congruent to angle CBD. Since this segment is bisecting this angle ABC, the two angles here and here must be congruent because that angle was bisected. It was cut into two congruent parts. So using the definition of bisector is important. All right, now be very careful. Why can you not conclude that ADB is congruent to CDB? This angle and this angle right down here. Are they congruent? Well, they could be, but do we know for sure? We don't have anything that says that ABC is bisected. So we don't know for sure if angle ADC is bisected too. It might be, but we don't have anything to prove that. So we don't know if ADC is bisected too, so we can't assume. So don't assume it is because it looks like it is. Don't assume. You can't say something is true unless you can prove it. Okay, now, also, if this is bisecting this angle, does it do anything to the segments AB and BC? Is AB congruent to BC? No, we're not cutting a segment in half, we're cutting an angle in half. So AB is congruent to BC is when you bisect an angle, you get two angles, not two segments. The sides of the angle are not what is being bisected. You get two congruent angles, not segments. So it's very important when you're dealing with definitions to be very precise and to apply what the definition says to your answer. So you should be able to, given a definition, draw a conclusion based on that definition and use proper terminology to get it. All right, that's all for today.